In our previous video, we finished with this theorem, that if we have a continuous function on a closed bounded interval, we're guaranteed to obtain an absolute maximum and an absolute minimum value on that interval. And so for basically the rest of this section, our goal is going to be try to find and locate and identify these absolute minimum and maximum values. And so before we get there, before we get to do that, we have to build our way up to being able to locate these absolute max and mins. And so let me draw a picture here before we get there. So here's some function f of x. And so there are a couple of points that I want to draw your attention to. So one is right here, one is right here, one is right here, and one is right here. And so the thing to realize is that for like this point to start off with, this is not if, let's say here, A to B, if we're thinking about this entire interval I, this is not the absolute maximum of our function on this interval. However, it is this value right here. So let's call it C here. This value f of C it's not bigger than everything else, because look over here, but it's bigger than everything else around it. And so in some sense, this is a maximum. It's a maximum as compared to the values that are just around it. We're going to end up calling this a local maximum. Similarly, let's call this D here. This is a local minimum. It's not an absolute minimum. Take a look, there's points lower over here. But for nearby values, things close to D, f of D is less than or equal to those values. Here we see another local maximum. In fact, this appears to be the overall absolute maximum here. Here we see another local minimum. And so so it seems like these points are important. So let me go ahead and show you a definition here for local extrema. So f of C is a local minimum or a local maximum. It's a local minimum at x is equal to C if f of C is the minimum value of f on some open interval containing C. So local maximum at x is equal to C if f of C is the maximum value of f on some open interval containing C. So going back here, f of C is the absolute maximum value on this little interval here. F of D is the absolute minimum value on this little interval here. So we're going to want to have this notion of local min and local max for what's coming up soon. So here's our definition of what local mins and local maxes are. So let's think about what's the interpretation of, or maybe not interpretation, but are there any properties, that's a better word, are there any properties of our local mins and maxes? Well, I start to draw a line here, but let's realize what's special about this point right here. There, the tangent line at that point is horizontal. Same thing here. The tangent line of that point is horizontal. The tangent line of this point is horizontal. Maybe we call that E here. And so horizontal tangent lines, what does that tell you? It tells you something about the derivative. It tells you that the derivative here is 0. The derivative here is 0. The derivative here is 0. And so there's one last point to note here. There's a cusp here that there's actually no tangent line. And so that's coming from, if this point, I'm running out of letters here, let's call this x naught here. F prime of x naught does not exist. So for our diagram, we had our different local maxes and local mins, and we see that every single one of them, the derivative of the function at that point is 0, or the derivative of the function at that point does not exist. And so that means that like where these that says here that the derivative equaling 0 does not exist is important. And so whenever we have something important like that, we want to introduce a definition here. And so we're going to call these points critical points. A number C in the domain of f is called a critical point if either the derivative is equal to 0 or the derivative does not exist. So something that we can do, let's do a problem right now. Let's go ahead and find critical points for a function. So let's find the critical points of f of x is x cubed minus 9x squared plus 24x minus 10. So how do we do this? We have to look at the derivatives. We'll take the derivative and set it equal to 0 and solve. So f prime of x is equal to 3x squared minus 18x plus 24. We want to set that equal to 0. We can factor out a 3 from everywhere. 3x squared minus 6x plus 8 is equal to 0. And that x squared minus 6x plus 8, that factors as x minus 2 and x minus 4. So we have two critical points. So these are the critical points. If we wanted to draw a picture, so the function looks something like this, where here is 2 and here is 4. So we see two horizontal tangent lines at x is equal to 2 and x is equal to 4, respectively. Okay, so I think that's a good place to wrap up this video. And at this point, I'll end it with our first pre-class problem. So mimic what we just did here. Here's a function, x cubed plus 3x squared minus 24x. We want you to find the critical points of that function.